Wonderful. Thank you, Claudia. Okay, well, thank you, everybody, for joining today. So we're going to be talking about test-driven graph modeling. And I've got some very practical examples. It's not a completely introductory session, so it assumes that you know perhaps a little bit about Cypher, and we're also going to be looking at some Java code a bit later on as well. Okay, so the first thing I'll do is just explain my motivation for the session. And it really comes down to my experience as a software developer. So when I'm building applications, there are a couple of things that are very, very important to me, and that's expressivity and flexibility. Expressivity and flexibility. So I'll talk a bit, first of all, about expressivity. When I'm building a piece of software, I want the code that I write, the models that I create, the schemas that I create, the data that I create, the queries and so on, to be expressive of the problem that I'm trying to solve. I want them to describe the business domain that I'm working in without any clutter, or as little clutter as possible. So I want as few additional language constructs, as few additional pieces of technology to intervene. I just want the domain to shine through as I'm building that software. And that allows me to communicate to all the other people that I work with, both developers and the other people within the team and our business stakeholders, what it is that we're trying to do and how we're going about solving some of those problems. So expressivity in software design and software development is very, very important to me. The second thing is flexibility. I tend to build software in an incremental and iterative fashion. Okay, so you start with a very simple application perhaps, but over time we're going to evolve it, we're going to introduce new requirements, and we're going to evolve that software so that it becomes more sophisticated, it addresses a larger range of requirements. Okay, and we're going to do that in an iterative and incremental fashion. Well, in order to be able to do that, I need my software to be soft, to be flexible, to be capable of being evolved very, very easily. Okay. So they're the two things that are really important to me, expressivity and flexibility. Now, as a software developer community, we've evolved a couple of ways of addressing these things. You know, there are specific practices that we adopt that help us create expressive software that's capable of being evolved. The first thing, with regard to expressivity, we tend to concentrate on things like domain-driven design. You know, domain-driven design helps us to identify an ubiquitous language that describes the business domain, and then we'll seek as far as possible to incorporate that language into the code that we write. Okay, so this is creating software that's expressive of the problem domain. The second practice that we adopt is test-driven development. So we use things like unit tests in order to drive out small pieces of functionality to capture in a programmatic form exactly what it is that we're trying to achieve with any particular functional component. And in doing that, in creating a large suite of unit tests, we effectively create a bedrock of asserted behavior. And this gives us the confidence to move forwards, to evolve our software over time. Because every time we make a small change, we can rerun that entire suite of tests, and we can see whether we're meeting all of our existing obligations, you know, sustaining existing functionality, or whether we've broken some functionality. You know, this gives us the confidence to make changes very quickly and to move forwards very, very quickly. So these are a couple of things that I'm looking for whenever I adopt a new technology. Does it allow me to create expressive software that's capable of being evolved easily? And so when I was introduced to graphs many years ago and introduced to Neo4j, these were a couple of the things that were back in my mind when I started using this technology. And I'm happy to say that I think we can use Neo4j today in a way that's incredibly expressive of the domain and allows us to build software that's very, very easily evolved, that's flexible, that's soft. So these are the things that we're going to be looking at today. It's kind of in two halves with a little bit sandwiched in between. In the first half of the session, I've got an example of how I go about actually modeling or creating an applications graph data model. So let's assume that you want to build an application on top of Neo4j. That application is going to incorporate its own application graph model. You're going to employ all of those graph primitives, the nodes, the relationships, properties, and labels, and so on, in order to develop your own application graph model and all the queries that you execute against that model. So we'll talk a little bit about the process that we can go through in order to derive that model and derive those queries from the problem at hand. Then the second half of the session, I'm going to look at how we can actually do all of that in a test-driven fashion. You know, sitting at a keyboard, writing lots of tests, unit tests, test by test, building out this application and building out our data model. Okay. The actual strategy that we employ with our testing is dependent on some of the application architecture choices that we make. So Neo4j can be incorporated into your app in several different ways, and depending upon how you incorporate it in the app, that will have an impact on the kind of testing that you do. So we'll look at some of those architecture options as well. That's the little bit in the middle. Okay. So let's look first of all at how we can actually go about deriving an application graph model from a set of requirements. The first thing I want to say here is something about the activity of modeling itself. You know, when we create a model, whether it's an object model or a relational model, or as in this case, a graph model, we're not trying to create a transparent window onto reality. We're actually creating a very purposeful abstraction. It's a purposeful abstraction of the domain that we're interested in, and it's there to satisfy a particular set of goals. You know, we've got a motivation. Somebody comes along, they present us with a problem, that's our motivation, a particular set of problems, and we design a model and an application that executes against that model in order to satisfy that particular set of goals. You know, and this is what Euler was doing several hundred years ago, you know, with the foundations of graph theory. He was creating a purposeful abstraction. You know, this is the 7 bridges of Königsberg problem. You've probably seen this many times if you've attended any kind of graph presentation. But it's a purposeful abstraction of the problem in order to satisfy or answer that question. Can I cross each bridge only once as I work my way around the city? So I want you to bear that in mind when we're talking about developing an application graph model. We're not just trying to create a transparent window onto reality. We need, first of all, to understand what's the problem we're trying to solve, and we'll use that to drive out the abstractions that we're going to use. So what we've got here is a very simple example application. It's a little knowledge management application. Let's assume that we've got a domain that comprises people and the companies that they work for, and then all of the different skills that those people have. We want to develop an application that allows us to capture all of this information. It's kind of cross-organizational application. It's going to store data about people, you know, from many different organizations. But it's also then going to allow us to identify our professional social networks. And we may want to do this, we may want to develop this kind of application in order to address these several different needs. We want to exchange knowledge with people who share some of our interests. We want, perhaps in a very large organization, we want to be able to form interest groups so that people can talk about specific technologies or talk about specific skill sets. They can help one another out. And we can also use that same information in order to staff projects with people with the requisite skills. So it's some kind of knowledge management application that we're imagining we're about to embark on building. Okay. So what I want to do here is just describe the process that I tend to go through when I'm working on applications like this. And the process that I go through is one where we take a natural language representation of the problem at hand. You know, what's the problem that we're trying to solve? And we slowly break it down and we translate each of those elements into elements within our model. So we start with a very simple English language description of the problem we're trying to solve, and then we're going to iterate over it until we can actually derive the specific graph elements and the queries that we need to execute against those elements. Okay. So as I say, if we're building an application in an incremental and iterative fashion, well, the way we do that, we typically have a backlog of requirements, of user stories, and they're probably prioritized. And we'll take each of those requirements in turn, you know, the highest priority requirements, and we'll use those to build out a small portion of our application. Then we'll take the next most important requirement and we'll evolve our application to meet some additional needs, the additional needs captured in that second requirement. So here we've got a single end user or application goal expressed as a user story. As an employee, I want to know who in the same company as me has similar skills to me, who in the company that I work for has similar skills to me, so that we can exchange knowledge. So here we've got a very simple description of the problem that we're trying to solve with this very specific feature within our larger application. Now, given this description, the first thing that we can do, or the first thing typically that I'll do, is turn it around a little. I'll start trying to identify the questions that I would need to ask of the domain in order to be able to meet or satisfy this goal. So we've got a description of the goal. We then start to think, well, what questions would I have to ask of the domain, and how would I answer them in order to be able to satisfy this specific goal? So we can take that description and we just twist it around a little, and we kind of uncover some of the questions we'd have to ask of our domain. And here's one of them. Which people who work for the same company as me have similar skills to me? We've effectively rewritten the requirement as a question or as a set of questions. And if we can answer these questions, then ideally we can actually satisfy this end user need. We can build an application that satisfies this requirement. So again, we're just working with a natural language representation of the problem at the moment, but in the form of a question. But given that question, we can now start to think, well, what are the things in my domain that I'm particularly interested in? What are the things that are important to me? What are the entities in my domain? Well, here we've got people, companies, and skills. They're the things that I'm interested in with regard to this particular question. In the singular, I've got a person, a company, and a skill. And then having identified those entities, we can begin to understand the ways in which those entities are connected to one another, the ways in which they're related. And again, we derive all of this from the questions that we want to ask of our domain. So we can see that a person works for a particular company, and a person has a particular skill. So again, some very simple natural language representations of the things that we're interested in and the ways in which they're connected. Now you notice here, I've kind of cheated a bit. I've described a person, has skill, skill. And the reason I've done that is because has or have is far too general a term. You know, I can have a skill, I can have a family, children, job, and so on. That's far too general a description. So I've kind of cheated a little and specialized the language that I use, but I'm still indicating that a person is related to a skill in a very particular way. Okay. So now we can take these very simple descriptions of the things that we're interested in and the ways in which they're connected, and we can convert those natural language expressions into Cypher path expressions. So the things that we're interested in, the entities, become candidate labels, and the ways in which they're connected become candidate relationship names. So I can take those two statements there and turn them into a couple of Cypher path expressions. So now you can see we're looking at what could potentially be a node labeled person that's connected to a node labeled company by way of an outgoing works for relationship. And then we have a node labeled person connected to a node that's labeled skill by way of an outgoing has skill relationship. And then with a little bit of refactoring, we can turn those two path expressions into a single path expression. A person works for a particular company and has a particular skill. Okay. So this assumes you know a little bit about the Cypher query language, but effectively we're creating a representation of the things that we're interested in and the ways in which they're connected. And we're identifying some of the labels that we would attach to the nodes in our domain, and we're identifying some of the relationship names that we'll use to connect those nodes together. So that Cypher path expression is effectively representative of this simple graph structure. A person works for a company and has a particular skill. Okay. Now that path expression, which we've derived from the question that we want to ask of our domain, that simple path expression is effectively the prototype for our data model. Okay, so we're dealing in the context of a single requirement here at this point in time. There's likely many more requirements that we'll want to introduce over time. But here and now, this is the basis of our underlying data model. If we can build an application that can stamp out multiple instances of this path, then effectively we'll have captured all the information that we need in order to be able to address this particular need. So you can see here I've got a little sample data set, and you can see that we've got multiple instances of this path. We can see that we've got a node representing Ian, who works for Acme and has the skill Java. Lucy works for Acme, has the skill Java. Lucy works for Acme and has the skill Neo4j, and over. Multiple instances of this prototypical path, we stamp them out over and over, and we build up a data set. So the path that we've derived from our user requirement becomes the basis for our underlying data model at this point in time. And then it's our job to build an application that, based on end user input, can actually populate the data set and stamp out multiple instances of this path. Okay. So we've derived our underlying data model, but we haven't completely satisfied that end user requirement. Because remember, we need now, given a particular user, we need to be able to identify, well, which other people in that company share that person's skills. So we go back to the question that we'd have to ask of our domain, and we want to formulate that as a query that we can execute against our model. So here's that question again. Which people who work for the same company as me have similar skills to me? Now, in order to be able to answer this question, given that little data set we looked at a moment ago, we're going to have to find multiple instances of this little diamond-shaped pattern. Somewhere in that data set, let's assume that there's a node that represents me. I'll be connected by way of a works for relationship to a node that represents the company that I work for. And I'll be connected by way of a has skill relationship to nodes that represent the skills that I have. We're looking for other nodes representing some of our colleagues connected to the very same company node and connected to the very same skill node that I'm connected to. And we're going to be looking for multiple instances of this. If one of my colleagues has 2 or 3 things in common with me, shares 2 or 3 of my skills, then we'll be looking to match this little diamond-shaped pattern 2 or 3 times on their behalf. Okay. So we've taken the question that we want to ask of our domain, and we've translated it effectively into a very simple pattern that we want to find inside of our data set. So we can take the pictorial representation of the pattern, and again, we can turn that into some Cypher path expressions and embed those expressions inside a Cypher query. So here we've got the entire query that helps answer this question. I'll just go through it bit by bit. The match clause is where we actually specified the pattern that we're looking to find inside the existing data set. So we're describing here that diamond-shaped pattern. You can see there's a node that represents me, and I work for a particular company and have a particular skill, and we're looking for colleagues who work for the same company and the same skill. And where we kind of duplicate those identifiers, we've got 2 instances of company there, 2 occurrences of skill. These things are pointing at the very same node. This is how we kind of tie these things together to create that diamond-shaped pattern. The where clause here helps anchor that pattern inside the existing data set. So what we're effectively saying here is we want to look through all of the nodes labeled person, and where the name property matches the name supplied to the query, perhaps we've supplied the name Ian, we want to anchor that particular node, or we want to anchor this pattern to that particular node. Okay. So the where clause is helping us actually anchor or bind the pattern to 1 or more nodes within the data set. And then the query will effectively flex that pattern around, looking for matches, rotating effectively around those anchor nodes. And then the return clause here is just creating a projection of the data that we're interested in recovering. Okay. So we're going to take each of those colleague nodes. If we find any nodes that represent our colleagues, we're going to take their name property and alias it as name. Effectively, we're going to create a tabular set of results, and the first column will be called name, and that will list all of the colleagues based on their name. The count function here then counts up all of the different skills that an individual has in common with us. Remember, I said if one of our colleagues has 2 or 3 things in common with me, then we'll match that pattern on their behalf 2 or 3 times. So effectively, we want to roll up some of the results here. We want to count the number of skill nodes that this particular person has in common with me. And then we're going to alias that number as score. So again, there's going to be a column in the results called score, and that's going to tell us how many things a particular person has in common with me. And then it's useful to know not only how many things somebody has in common with me, but also which specific skills a person has in common. So this last element here, collect, the collect function, effectively creates a comma-separated list of all of the skills that that particular person has in common with me. And then we're ordering the results based on score, highest score first. Okay. So if we imagine how this would actually execute against our little sample or toy graph, well, there on the right-hand side of the screen, you can see the pattern that we're looking to match. If we actually execute the query against our sample graph, well, here's our first match. Ian works for Acme, has the skill Java. Lucy works for Acme and has the same skill. Here's our second match, second occurrence. And again, it's based around Lucy. Both work for Acme, but this time we both have Neo4j in common. And then the third match, Ian and Bill, they both work for Acme. Ian and Bill both have the skill Neo4j. Okay. So if we actually execute that Cypher query against the data set, if we're able to build an app that can build out that data set, if we execute this query against it, these are the kind of results that we're going to get. And as I said, we're creating a kind of tabular set of results with columns called name, score, and skills. You can see that Lucy's got two things in common, Java and Neo4j. Bill has one thing in common with me, which is Neo4j. Okay. So what did we do? I mean, this is a very, very simple example, but hopefully it gives you some insight into the kind of process or the kind of techniques that you can apply in order to derive that purposeful abstraction. We started with an end-user story, with a description of the problem that we were trying to solve. And then we kind of dug inside of that story a little bit in order to identify the questions that we would have to ask of our domain in order to satisfy that end-user goal or that application goal. So we translated the user story into a set of questions, or in this case, a single question. And then based on that question, we started identifying some of the entities and the ways in which those entities were related. These are the things in our domain that we're interested in and the ways in which they're connected to one another. We then took that very simple description and translated that in turn into a series or a set of Cypher path expressions. And this gave us our prototypical path construct. This was the basis for our underlying application graph model. Right? And the assumption is that we can then build an application that can stamp out multiple instances of that pattern over time as we learn more about the people that we work with, the companies where they work, and the skills that they have. And then we returned to the question, and this time we translated the question into the kind of query that we could execute against the model in order to satisfy this end user goal. So the interesting thing here is the way in which the underlying domain model or the underlying graph model and the queries that we execute against it, well, they're effectively two sides of the same coin. We derive them both from the question that we wanted to ask of the domain. So it's no coincidence that the path expressions in our match clause, the path expressions in our query, look very, very similar to the path expressions that we used to create the data set in the first place. And this is very, this is a good test of whether you're building a good model and a good set of queries. If the path expressions in your queries look very similar to the path expressions that you used to build the data model in the first place, well, you're probably on the right lines. But if you're creating a model based on one set of path expressions and then you're coming up with some very arcane or weird going around the houses kind of path expressions in your queries, then there's a mismatch here. The goal with building our purposeful abstraction is to design for queryability. And the queries are always derived from the questions that we want to ask of our domain. Okay. So we do need an understanding of the problem that we're trying to solve. It's often nice just to think, well, I'm interested in this domain, I'll capture all that information, and then I'll think how I'll apply it. But far better if you can understand in the first instance, well, what's the real problem I'm trying to solve? Okay, now I'm going to be a bit more specific, a bit more targeted about the kind of model that I create and the kind of queries that I execute against it. Now, this may sound as though we're overly specializing the model and the queries for that particular set of requirements, but in a way we are. I'm fine with that. I'm confident that the graph itself can be very easily evolved and adapted to meet other needs and other requirements. And as we'll see with some of the unit testing, I'm actually going to provide myself with that bedrock of assertive behavior that gives me some very, very rapid feedback whenever I start introducing new requirements and start wanting to change the model. Okay. So that's a very, very quick overview of the graph modeling process, as it were, deriving your model and your queries from your underlying business requirements. Okay. So in this second session, we're now going to, or the second half of the session, we're going to look at some of the testing strategies that we can employ. So we can do a lot of what we've just looked at on the whiteboard, but ideally I would want to be sat in front of the keyboard sooner rather than later and actually building out some of these queries and writing tests around them to give me some very rapid feedback and some confidence that what I'm imagining at the whiteboard actually translates into something that works with Neo4j. So that's one of the good reasons for creating unit tests and for doing test-driven graph modeling. We want to ensure that the model that we're creating is fit for our domain, matches our understanding of the domain, and is fit for the queries that we want to execute against it. And we want to get very rapid feedback about our understanding of the mapping from the natural language representation all the way down to the graph. So the sooner we can work out whether the model and the queries work together in harmony and help us really answer those questions, the better we're going to be. Tests are a long-lived artifact. They live with the rest of the code. They're going to live for the lifetime of this application. So they're a great place to document in a programmatic fashion our understanding as developers or data architects. Great place to document our understanding of the domain. Right? And it allows us to also document a lot of the weird corner cases that inevitably arise. Okay, so we can write specific tests that capture some of the weirder pieces of data that inevitably creep into our domain. And allow us to exercise some of the more obscure queries that nonetheless are perhaps important to our application. And then finally, as we build up that suite of tests, we're effectively providing ourselves with that bedrock of assertive behavior. It's a regression test suite. And if we can run it over and over again, many times a day, every time we check in some code, then we'll get some very rapid feedback as to whether the changes we're making now, as we're introducing new requirements or new pieces of functionality, we'll get some very rapid feedback as to whether those changes have broken existing functionality. And if we spot any breakages, we can go and repair them sooner rather than later, rather than have our end users discover those problems. So this gives us the confidence to change and evolve the model, and the queries that we execute against the model gives us the chance to evolve them over time. So the overall method that I tend to employ when writing these tests is to encapsulate my queries as little objects or classes. So encapsulate the queries inside an object that we can then exercise within a unit test. And within that test fixture, I'll create a very small, well-understood data set, a data set that I control, that I populate. And I'll create an instance of that inside of my test fixture, and I'll inject it into the object under test. So I've got complete control over the test data as I set it up, and I'll inject that into the object under test, the object that encapsulates my query. And we can do that using a version of Neo4j that we provide in our test jars, an in-memory version of Neo4j that allows us to set up and tear this stuff down very, very quickly. And we'll look at that in a moment. Okay. And then I can actually write unit tests in my programming language that exercise the object that encapsulates my query, and I can assert the results. Given that I've controlled the data going in, I understand which data I expect to come out of the query, and I can make assertions against that data. Now, the exact testing strategy that we choose depends in part upon the application architecture that we've chosen. So I'm going to talk very briefly about these application architecture choices, and then we'll actually look in more detail about, as an example of unit testing some of these queries. So Neo4j can be incorporated into your application in several different ways, and I've listed 3 of them here. we can run it as an embedded graph database. We can run it as a server product, and we can run it as a server with some additional code that you supply that sits inside of the server, these things that we call extensions, that do some additional arbitrarily complex functionality on the server side, very, very close to the data. Depending upon which solution you choose or which architecture you choose, well, this will have an impact on the way in which you write your tests. Okay. So embedded, as I say, an embedded graph database, this is the foundations of Neo4j. Neo4j started many, many years ago as an embedded graph database. And what this means is that you can host the database engine in your own Java process, in your application's Java process. And then you can use a rich set of Java APIs in order to create and query data inside of the database. Okay. So the database is effectively sitting side by side with the rest of your application code and executing in the same process as the rest of your application. That's all well and good, and as I say, it gives you access to that wide range of Java APIs, to some of the lower level Java APIs. But that's not our typical experience of a database today. I mean, more often than not, we expect a database just to be sat on some server somewhere else on the network. And irrespective of the programming language that I'm using to develop the application, you know, I ought to be able to connect to that database. I just want a client driver, and I want to connect over the network to create and query data inside the database. So the way in which the majority of people use Neo4j today is in server mode. Okay, so many years ago, we created the server version of Neo4j. We effectively created all of the server infrastructure that wraps an embedded graph database instance. We created all of that server infrastructure on your behalf. So you can stand up a server or a cluster of servers and then connect to them over HTTP. So the way in which you create and query data is by exchanging JSON formatted documents over HTTP. And almost any, pretty much any programming language today provides you with a simple HTTP client. At the basis level, you've got all the tools you need to connect to a server. But of course, there are lots of specific client drivers out there, some of them developed by Neo ourselves, and some of them developed elsewhere in the community that provide you with some of the client-side functionality that allows you to connect to that server. The third architectural option here is running Neo4j as the server version of the product, but adding to it, introducing some additional functionality into that server in the form of extensions. Okay. So you can write some simple Java classes, and we'll look at an example in a little while, that sit inside of the server and execute against the embedded graph database that's at the heart of that server. And the advantage here is of using these extensions, they allow you to encapsulate particularly complex logic there on the server side. They allow you to do additional work there on the server side, perhaps calling out to other systems. They also give you a high degree of control over the HTTP request response format. So you can control all of the HTTP headers, and you have complete control over the request and response format. So if you're using the vanilla server product, effectively you're constrained to using JSON over HTTP. And the responses that you return pretty much talk in terms of the graph. They talk in terms of nodes and relationships and properties. But if you're using extensions, you're not confined to that. You could choose an alternative representation format, XML, some binary format, if you so choose. And you can also create responses that talk more in terms of your domain, whether it's products and users, and so on, rather than in terms of nodes and relationships and properties and so on. Okay. So these are some of the different options that you have when you're building your own application on top of Neo4j. So the examples that I've got next show how we can develop against an embedded version of Neo4j, and then the second example shows how we can develop a server extension and to do all of this in a test-driven fashion. So here's the embedded example. Okay. Now both the examples actually refer back to the work we did in the first half of the session, where we were building up our simple knowledge management domain model. Okay. So it's the very same example, really. It's a company social network, and we want to find those colleagues who have similar skills. Okay. So we're going to take the query that we worked on in the first half of the session, and now, in this embedded example, we're going to encapsulate that query in a ColleagueFinder object. Okay. So the ColleagueFinder is going to encapsulate our query, it's going to execute against an embedded graph database, and then return the results to the client code. Okay. So this is what our unit test fixture looks like. So I'm going to do this TDD. I'm going to create a test fixture and write one or more tests. In fact, I'll write a first test, and then I'll start writing the object under test. You know, the very last thing that I'll do is actually start writing that ColleagueFinder object once I've set up all my test infrastructure and some sample data and actually described the particular piece of functionality that I want to test here. So this is the basis of my unit test fixture. This is some Java code here. And I'll just go through this in a bit of detail. So in the setup for the test fixture, we're going to create an impermanent graph database. This is an in-memory version of Neo4j. Okay, it's a fully featured version of Neo4j, but it runs in memory, and it's there purely for testing purposes. We use it internally throughout a lot of our development, a lot of the tests that we write when we're developing the product. But we also make it available to you in a test jar so that you can use it in your own unit tests. So we're going to create an instance of an impermanent graph database, this in-memory graph database. We're going to assign it to a member variable within this test fixture. We're then going to populate it with some sample data. And it's going to be a very small sample data set. It's effectively going to be that little pyramid-like data set that we looked at earlier. And then we're going to create the actual object under test, our ColleagueFinder. Okay, now remember, at this point in time, we haven't actually written any ColleagueFinder code. So you know, a lot of this is going to be read perhaps in our IDE, but we're very quickly going to get around to writing the ColleagueFinder itself. But this ColleagueFinder is the thing that actually encapsulates our query. And into the constructor of that ColleagueFinder, we're going to inject a Cypher execution engine. So the execution engine just wraps the embedded graph database instance. It allows us to execute Cypher queries. We're going to create one of those execution engines and inject it into the ColleagueFinder. Okay. So here's that, you know, some details about the impermanent graph database. It's an in-memory version of Neo4j. It's used purely for testing purposes. We don't warrant it for production in any way whatsoever. But it allows you very quickly to start up an instance of Neo4j and tear it down. Okay. And if you're using Maven, there's some of the details that you might need in order to be able to grab hold of that. As I say, it's in our test jar that ships with the binaries. Okay. Now in that test fixture, what we were doing in the setup, we were creating the impermanent graph database, and then we were populating it with some sample data. So here we've got the little method that will actually create our sample data when we start up this test fixture. So we're using a Cypher create statement here in order to create all of the nodes and properties and the relationships that represent that little pyramid structure that we looked at earlier in the session. Okay. So that's populating the data set. By the time the setup completes within the test fixture, we've got an instance of Neo4j running, and we've populated it with a little bit of data. Now we can actually start writing our tests. Okay, so I'm going to write a first unit test here. This test is called should find colleagues with similar skills. Okay, so this is all part of the same test fixture, and this is going to execute once we've done all of that setup. So the first thing we're going to do is call the findColleaguesFor method on our ColleagueFinder. Again, we haven't written this method yet, but assuming that that's the next thing that we'll do, we're going to call its method here. We're going to pass in the name of a specific user, and then we're going to assign the results to a local variable here, to the results variable. And then in the remainder of the test, we just make some assertions against the contents of those results. So remember, because we were populating the database with a well-understood data set, we completely control the data here. We know exactly what results to expect when we execute this ColleagueFinder. So expect Lucy to be the first result that we got back, because she had two things in common, and then Bill. So we've got a couple of assertions here. And then we've got this last assertion. This is a very, very important assertion. This checks that there's no more data. We want to check that we get the data back that we expected, but we also want to check that we don't get any data that we didn't expect. Okay, so we've got 2 lines in the results, and there was nothing else. Okay, so that's our first test. We then have to make this test pass by actually implementing our ColleagueFinder. So here's the beginnings of our ColleagueFinder object. This is a thing that encapsulates our query. Okay. So here's the constructor. Remember, in our test setup, we were injecting a Cypher execution engine into an instance of a ColleagueFinder. So here you can see we've injected it into the constructor, and we've assigned it to a private member variable. So it's available to all the other methods in the class. Okay. And at last, we can now get round to actually implementing our findColleaguesFor method. Here it is. Okay. So we're going to pass in the name of the person for whom we want to find all of their colleagues and the skills that they have in common. And we're going to return a set of results. Here we've just got an iterator containing an iterator of maps, a list of maps. So it's a very simple implementation, but what we've done here, we've taken the query that we worked on a little earlier in the session, we've put that inside of our object, we've parameterized it, so we've taken the name that's passed into the method, and we've used that to parameterize the query. This is very, very important. By parameterizing the queries, we allow the query plan itself to be cached in that execution object. So actually creating the query plan is a relatively expensive operation, but if we only have to do that once, and then we can parameterize the actual queries, we'll get far better performance as we execute this query over and over again in the course of the application lifecycle. So we're parameterizing the query, we're executing it using the execution engine, and then we're returning the results. And that's it. We've written our first unit test. Okay. And we did that by creating a small sample data set using an ImpermanentGraph Database that contains some of that data and injecting all of that into the object under test. So that was the embedded graph database example. Okay. In this last bit here, we're going to look at how we can do something similar, but this time using the server version of the product and using an unmanaged extension. So this is where we create some of our own code that's sat there on the server and runs close to the embedded graph database that sits inside of that server. Okay. So it's going to be the same data model and the same query as before, and in fact we're going to reuse that ColleagueFinder, but we're now going to host that ColleagueFinder inside of what we call an unmanaged extension, so we can actually expose it to the outside world over the network. So server extensions, these unmanaged extensions, very simple bits of code that you can write. You just supply a few annotations, and then once they're compiled, you can actually place them inside of the server. Effectively, what you're doing is creating RESTful resources. So you're creating a little resource that will be invoked over HTTP. We're going to dispatch certain HTTP requests directed to particular URIs. We're going to direct them to instances of your unmanaged extension. And we're going to strip out data from the request, perhaps from the URI or from the body of the request, and pass it into the instance of your unmanaged extension so that you can execute it against the embedded graph database there inside the server. So all unmanaged extensions use these things called JAX-RS annotations. JAX-RS is just a Java programming API that allows you to create RESTful resources. These annotations effectively map particular parts of the HTTP request to instances of your object and particular methods in your object. Okay. So the path annotations here are mapping particular parts of the URI space to our unmanaged extension. So our unmanaged extension is going to be hosted at URIs that begin /similar skills. So any HTTP requests directed to the server that begin /similar skills will be directed to an instance of this unmanaged extension. And then we've further annotated the actual get colleagues method here with an additional bit of the path, and then this is allowing us, the path parameter annotation is effectively allowing us to strip off the last part of the URI and turn that into a parameter that we pass into the method. So we're effectively dispatching a particular request, in this instance an HTTP GET request to similar skills /Ian. We dispatch to an instance of the extension. We'll strip off the Ian value at the end of that URI and we'll pass it into this getColleagues method. This is the kind of thing that you have to do when you're developing an unmanaged extension, using these annotations in order to effectively situate them within the URI space. Okay. The other thing to note here, so this is, I've kind of started backwards here. I'm showing you an example of the object under test before we've written any of the tests, just so that you get a sense of what's involved in creating an unmanaged extension. The other part here is the constructor, again, and the @context annotation here. So remember, this is an unmanaged extension that's running inside of the server. And at the heart of that server is an embedded graph database instance. The server is just all the infrastructure that surrounds an embedded graph database instance. This @context annotation allows us, or allows the server to pass either a direct reference to that embedded graph database or references to some other ancillary objects into your unmanaged extension. So here we're using it, the @context annotation effectively ensures that the server will give to us, will give to an instance of our extension, it will give us a Cypher execution engine. So there's a long-lived Cypher execution engine that belongs to that server, and that will get injected into this unmanaged extension instance. And then we can use that to new up an instance of our ColleagueFinder, the ColleagueFinder that we developed and tested against an embedded graph database a little earlier in the session. We can new one of those up based on that Cypher executor or the execution engine there, and again assign that to a member variable inside of our unmanaged extension. All right. The getColleagues method itself is where we execute our ColleagueFinder. We're taking the value that's been passed in, the value that's been stripped off the end of the URI, perhaps it's Ian. We're going to pass that into our ColleagueFinder, much as we did in our previous test. We're going to get the results, but this time we're going to format the results as some JSON, and we're going to return that over the wire. So we're generating a 200 OK response with a JSON formatted body containing the results of that query. Okay. So this is what the extension, the unmanaged extension test fixture looks like. Very similar to the previous test fixture that we were writing, but whereas in the previous test fixture we were creating an impermanent or in-memory graph database, here we're creating an in-process server. Okay, so we're trying to start up a lightweight server instance, host it in the same process as the tests that we're executing, but that server will contain our unmanaged extension, and within our tests we'll actually be able to exercise it using an HTTP client. Okay. So here in the setup, we're using a server builder in order to create the configuration for the server and to start it. So we're supplying some configuration information here, saying that, look, anything, so this with third-party JAX-RS package instruction here is saying when we start the server up, I want you to scan all of the jars on the class path, and anything where we have the package org neo4j good practices, I want any of the objects that you find there, I want you to host them at this, what we call a mount point, at this root URI /colleagues. So we're going to mount our unmanaged extension at this URI /colleagues, and that will become the basis for the part of the server space that our unmanaged extension occupies. We then start the server, and then much as we did in the previous test, we actually populate it with some sample data, and we can use the very same method that we used previously to populate this with a little bit of sample data. And then in the teardown, in the after statement, we actually stop the server just to clean up. Okay. And here, I mean, you'll be able to get hold of these slides after the webinar, but again, here are some of the details that you need in order to be able to get hold of one of those server builders And again, this is purely for testing purposes. It's not really for production use, but it allows you to host the server inside of your own process, inside of your test process. Okay. So we've created our test fixture. We can now create a unit test that begins to exercise our unmanaged extension. And the process here is slightly different. We're not going to go direct to the unmanaged extension. Instead, we're going to create an HTTP client, and we're actually going to issue a GET request against the server that's running. Okay, so we've got a server up and running as part of this test, or as part of the test fixture. We're going to issue an HTTP request against it, and then we're going to make some assertions against the response that we get. Okay. So we create an HTTP client, and then we issue the GET request. So we're issuing a GET request against HTTP localhost 7474/colleagues/similar-skills/Ian. So you can see the /colleagues bit, that was our mount point. So we've mounted our unmanaged extension at that portion. And then the /similar-skills/Ian, well, all of those annotations are going to come into play to effectively dispatch this particular request to our unmanaged extension. Okay. And then we capture the response, and we can parse out the JSON body that's contained within that response and make some assertions against it. Okay, so we've captured the response body, and then we actually make some assertions against the response. We check that the status code, the HTTP status code, was actually 200 OK. We check that it was accompanied by a content type header that said application JSON, and then we actually create a couple of assertions against the contents of the response. And again, we probably ensure that we've only got the data that we were expecting and nothing more. Okay. So, I mean, that's a kind of whistle-stop tour of the design and the test process. We looked at the way in which we can, starting with a set of end-user requirements, a set of application or end-user goals, we looked at the way in which we can break them down, begin to identify the things that we're interested in, the ways they're connected, and from them derive the path expressions that become the basis of our model. We looked at how we can return to those questions, the questions that we need to ask of our domain, and from them derive the queries that we need to execute against our model. And then we've had a brief look at the way in which we can actually encapsulate that model and some of those queries inside of our unit tests. And we'll build up a large suite of unit tests as we build out our application, as we introduce new requirements. And this gives us the confidence to move forwards as quickly as possible. And I think between them, these two strategies effectively address my needs around expressivity and flexibility. The data model that we've come up with is a very clear abstraction that maps very nicely onto our domain, onto our business problem. And it's not really cluttered by anything else. There isn't a lot of additional unnecessary detail there in the model. It really talks about the things that we're interested in and nothing else. Similarly, I mean, I think the Cypher Query language is a great way of expressing in a very compact but very readable form the kinds of questions that we want to ask of the domain. And then the unit testing, much as with TDD in general, allows us to develop all of this stuff bit by bit and create that bedrock of assertive behavior that allows us to evolve an application over time. So that's the end of my talking. There are more details around this in the Graph Databases book itself. And I think most of the examples that we've seen today, you can also grab from my GitHub account. There's a project there called Neo4j Good Practices, and it's just got some very simple, all the examples that we saw here, together with some other stuff that I've written that illustrate effectively testing strategies. Okay.
Thank you ever so much, Ian. That was great. I think we have another couple of minutes to look at some of the questions. Ian, can you see the question panel? Otherwise, I'll read out some questions to you.
I can see a question panel, but I can't see any questions. So I'm assuming you
can
see
questions. I can. Yes. So one question is, what's the advantage of using a server extension versus using an application layer on top, such as Spring or Rails?
I think these are complementary strategies. It's not necessarily an either or choice. So an unmanaged server extension allows you to encapsulate particularly complex logic and to run it very, very close to the embedded graph database. Now, if you've got a particular end user operation that perhaps requires several requests to the server, you need to do some reads and some writes before you can complete that end user operation. Well, you could encapsulate all of that in an unmanaged extension and encapsulate it all in a single request response cycle. So as long as the end user can supply all of the information necessary for that particular operation, you could do all of that work close to the embedded graph database and then generate all of the response, all of the results, and return it to the client. Whereas if you were developing or implementing large parts of that operation further up the application stack, then there'll be occasions perhaps where you have to issue several requests. I want to learn a bit about the data as it stands today. I want to make some decisions and then modify the data and so on. And that's several requests and responses. We can encapsulate all of that inside the unmanaged extension. And if I've got Java skills, I mean, it does require you to be on the JVM and finally to be writing Java here if we're writing an unmanaged extension. But it allows me to start simple. I create an object, much as I would if I were working against an embedded graph database. I create a class that encapsulates my query, and I can use Cypher, or I can use some of those lower level Java APIs, what we call the core API or the traversal framework, in order to implement that underlying functionality. So it gives me a range of options, all of which are masked from the rest of my code, from the rest of my application. Because I can actually swap out the underlying implementation. I can move from the traversal framework to Cypher, if necessary, without the client ever becoming aware of it. And then the last advantage is, we can also talk to other systems, to other back-end systems if necessary. So again, encapsulating a complex piece of logic that may actually require us to query another system or to manipulate another system, and to do all of that perhaps in the context of a single transaction. But I think it then complements other parts of the stack. You still might be using Spring Data Neo4j or some Rails framework, and they can talk. You don't have to implement the entirety of your application as an unmanaged extension. Perhaps you just pick out the bits that are very performance sensitive and move them into an unmanaged extension. And then the remainder of your framework is talking to the vanilla server API and only occasionally going off to use one of these unmanaged extensions. Hopefully that's answered the question.
Okay, another question is, how do you combine various tests?
How do I combine various tests? Okay, so the fact that I was creating a little impermanent graph database, this little in-memory graph database inside of each test fixture gives me a high degree of isolation. So within each test fixture, I can just, I'm spinning up a new instance of a database. I'm just populating it with the data that's relevant to that particular test or that suite of tests. And so that gives me a lot of isolation. I can develop other test fixtures to address other needs, and that gives me a high degree of separation. I could, if necessary, have some common code that's going to populate all of my test fixtures with the same underlying data set, and that's going to give me the confidence that all the different queries that I'm writing all work against the underlying model. One of the things that I haven't talked about here, but I think there's the beginnings of it actually in the GitHub project, is the way in which we can also introduce migrations. So this is, again, as we're developing our application over time and evolving it, we may discover occasions where we need to actually change the underlying data model, to change some of its structure. We need to be able to refactor the graph. Perhaps we discover that what we previously modeled as a relationship should ideally, we need to be able to pull out a node. So we need to model it as two relationships and a separate node. Well, that's the kind of refactoring that we probably need to do against an existing graph structure. And again, some of the examples in that project show how we can begin to introduce these migrations, effectively introduce incremental changes to the underlying structure while still ensuring that all of the tests continue to pass. If something breaks, then we know that that migration, it's a necessary migration, but we need to go and fix up some of the functionality elsewhere. So it's about, for sure, it's about being able to combine stuff, but it's also about being able to separate out some of the testing. So we've got little isolated silos of data where we're not stamping on one another. Each test isn't stamping on the changes made by some other test. And the benefit of using an impermanent graph database, we can do all of that very, very quickly without really having to, to spin up the entire database infrastructure and then tear it down with each test.
So one more, maybe a bit more general question here. Is there any limitation on how many nodes you can have without affecting performance?
Is there a general limitation on the number of nodes? Okay, so query performance is really a function of the amount of the graph that you have to search, or that you're prepared to search, in order to answer the question that you want to ask in your domain. Okay. So it doesn't matter whether I've got modulo some IO, because finally we are going back down to disk when we're dealing with the real database. But modulo some IO, it doesn't matter whether I've got 10,000 or 1 million or 10 million nodes in my database. If, in order to answer a particular query, I only actually have to crawl or traverse a couple of thousand nodes, because the rest of the graph will effectively be grayed out. The advantage of the queries that we write, are looking for particular relationships to follow, and they're ignoring all the other relationships because they don't match the relationship name specified in the query. And we're binding those queries to specific nodes in the data set. So we're effectively parachuting into the data set and then just crawling the surrounding area. If the data that we want is in that surrounding area, it doesn't matter how much data there is elsewhere in the graph. That's really not going to impact the query performance. So the performance itself is a function of the amount of the data set that we have to search. It's not really a function of the overall size of the database.
Mm-hmm. Thank you very much, Ian. I'm afraid to say that's all we have time for today. I know there's still a lot of questions unanswered, and I do apologize for that. We will send a link to this webinar recording to you in the next 2 days, so you'll get that from us. Apart from that, please look on our website. We have loads of events across the globe, training, meetups, conferences, maybe something that's on your doorstep if you want to find out more about Neo4j. We would be very happy to see you somewhere face to face. Thank you very much to everybody for joining us today. Thanks very much, Ian, and have a nice day.
Thank you. Bye-bye.
Bye.